Hello everybody. I wanted to go ahead and start, make another video where we kind of walk through module 1.2 and the material that we covered that. That includes our shell model of an atom. And so when we're talking about the shell model, we talk about ionization energies and atomic radius. So I wanted to try to address some of those topics and maybe hopefully clear up any sort of confusion associated with them. Radius. At any rate, I'm going to go ahead and get started. So, just a second. Okay. The first thing that I want to talk about is potential energy, and specifically the Coulombic potential energy, PE, which we know the Coulombic potential energy equation to be V equals K Q sub 1, Q sub 2 over D, our distance. Okay, so let's define everything here. K is a proportionality constant. Q sub 1, sorry, that looks like 2. Q sub 1 is the charge on a particle. For instance, an electron is going to have a charge of -1. A single electron will have that charge. Q sub 2 would be the charge on another particle. Oh, I spelled particle wrong. Well, now it looks like, anyway, particle on a particle. And in the case of something like a proton, it would be +1. Multiple protons are going to have multiple positive charges. And then finally, lowercase d is our distance. So the distance between these two entities, the distance between these two particles. The proportionality constant is going to vary from atom to atom. We looked into this and we looked into understanding this in a fairly simple way by looking at a one proton atom, and so our Q sub 1 is +1, and that one other particle was an electron, and so our Q sub 2 was negative. Now, if we talked about something like a carbon atom or something like that, carbon has 6 protons. So if we were to look at the Coulombic potential energy equation, our Q sub 1, for instance, would be 6+, because we have 6 protons. Okay, so what this is ultimately used for is to explain something known as ionization energy, which ionization energy is the energy required to remove one electron. Okay, now our ionization energy, we related that to the Coulombic potential energy V, and what we found was that our ionization energy was equal to, so our negative V was equal to our ionization energy. So if we included or required X amount of energy to remove a single electron, we could relate that to our Coulombic potential energy. So on this page right here, I have a slide, or I have a screenshot that shows the first ionization energies, IE sub 1. So that's the energy required to remove our first electron. Okay, now all of this is empirical data. This is experimentally determined, EXP, experimentally determined. So this is all. So let's focus on two elements. Our first element is going to be hydrogen. Our second element is going to be helium. Okay. Now hydrogen has a single proton in the center of its nucleus. Helium has a total of 2 protons in its nucleus. Now, this data right here was used to ultimately come up with a model for what these electrons look like, or what an atom actually looks like. Okay, so this model proposes that one proton in hydrogen pulls on or attracts one electron outside of that nucleus. Helium, on the other hand, has a total of 2 protons and a grand total of 2 electrons. Okay. Now what we see is an ionization energy, IE sub 1, for hydrogen as 1312, and an IE sub 1 for helium as 2373. So effectively what that means is it takes more energy to remove one of the 2 electrons from helium compared to the single electron from hydrogen. So more E to remove first E from, I'm sorry, that's a lowercase e, from H than HE. Okay? Sorry, from the first electron of HE. Why is that? Well, one of the factors that we have in play is we have the difference in the number of protons. So we have 1 proton in our nucleus for hydrogen compared to 2 protons for helium. So basically what that means is that, or what that could mean is that at any given point in time, each electron in the presence of, each electron in a helium atom is going to feel not just the force of 1 proton attracting it, but the attractive forces of 2 protons combined. Okay, so that's the first idea. Now, a development of that model kind of asks you, well, if that was true, what would you expect to see for IE1 of lithium? And now, without looking at the data, let's kind of draw that up. That would suggest that we have 1, 2, 3 protons in the center of our nucleus, and then we have 1, 2, 3 electrons in the same space, in the same shell, the same distance from our nucleus. So what would that mean? Our distance has not changed. If we think back to our potential energy equation, we see V equals K Q sub 1, Q sub 2 over distance. Now, if our distance has not changed, if these electrons, these 3 electrons, are the same distance from our nucleus as the 2 electrons in a helium atom are from the nucleus of helium, then what does that mean? That would mean that since the distance hasn't changed, we could expect our IE1 for Li to be higher than that of HE. Okay, so that's what an expectation would be if this shell right here, this little spherical area that these electrons exist in, if that were the case, then that would be a reasonable expectation. Now, when we look at our data, what do we see? We see that the IE1 of lithium is considerably lower. It drops off. It is actually 520. So what does that mean? That effectively means that this third electron, I'm just going to highlight one of them down here, this third electron right here, well, it's not feeling the same force as the first 2 electrons in a helium atom or the first electron in a hydrogen atom. So what does that mean for our model? That means that our model has to evolve a little bit. So our evolved model for a lithium atom could effectively look like this. 1, 2, 3 protons, 2 electrons in this first shell, this first area around our nucleus, and then our third electron Well, it has a lower ionization energy and a lower IE, in part IE1, resulting from electron number 3, I'll just call it electron number 3, being farther from the nucleus. Okay, so then it kind of asks, or you can kind of look at your other information and say, all right, well, I'm proposing that we have a new shell outside of our inner shell. So what would we expect to see for something like beryllium, the next element in the periodic table? The Be, we would expect 1, 2, 3, 4 protons, 2 electrons in this first shell, and then 2 more electrons in this next shell. And if we've got 2 more electrons in this next shell, well, each one of them is going to feel at most the force of 4 protons. We would expect the ionization energy, IE1, for Be to be greater than that of IE1 of Li. Now, with that idea in place, we can look back at our data. Lo and behold, our data shows that our IE1 for Be is, in fact, higher. It's 899 compared to the IE1 of lithium is 520. So for this next development of the ionization energies, I want to point out a couple of different atoms: lithium, sodium, and potassium. Now when you look at these on the periodic table, and here's my crude diagram of the periodic table, all 3 of these atoms are going to be found here in this general area. This is known as group number 1. And I'm going to go ahead and draw rough representations of them. Okay, so for protons, I'm just going to indicate 3 plus for lithium. We've got a pair of electrons, and then we've got this outer sphere where our third electron is going to be found. For sodium, we've got, that'll be 11 protons. We've got 2 electrons here, 2 electrons here, and then in this next sphere, we're actually going to be able to place 8 electrons. Four, 5, 6, 7, 8. Now, why is it that we were able to do that? Well, one thing that I want to draw your attention is that when we move across the periodic table from left to right, that's the same as movement from lithium on down to neon. What do you see there? What you notice is that our ionization energy slowly but surely and steadily creeps up. Once we hit a total of 10 electrons placed around our nucleus, well, for placing that 11th electron, our ionization energy drops off. So think about a parallel between neon and sodium as being similar to helium and lithium. Once we filled our shell, then the addition of our new electron, well, it had a lower ionization energy. So for lithium, we put that 3rd electron into a new shell, and for going from neon to sodium, we're going to put our, in this case, 11th electron in a 3rd shell. Okay, now the next atom, is potassium. So what potassium is going to have is 19 protons, electron, electron. Then we've got 1, 2, 3, 4, 5, 6, 7, and 8 electrons. So that's 10 there. Our next shell is going to have 8 electrons as well, because again, when we look at argon's ionization energy, moving to potassium, we see another drop off. So there's 2, 3, 4, 5, 6, 7, 8, and then a 4th shell here is where we're going to place our 19th electron. Okay, so when we look at these, first and foremost, there is a simpler way to draw them. One is that we have to identify some of our different electrons. So the electrons in the outermost, so outer electrons, are known as valence electrons. So when you think about each one of these atoms, all 3 of these being Li, Na, and K, they all have 1 valence electron. Now, let's look at the ionization energy, the first ionization energies of all of these. So Li, Na, and potassium, and K. These ionization energies are 520, according to this chart, and this is never some number that you'll have to memorize, 495.9, and potassium is 418.7. 418.7. Okay, so what's kind of interesting about this is that all of these ionization energies are going down. So when you think about why is that, one thing I'd like you to do is think about our Coulombic potential energy equation, which is V equals KQ1 Q2 over D. And what is that? That's our distance. So what has happened in each of these 3 models? That outermost electron, that valence electron, what has it done with respect to the nucleus? It's gotten farther. So it's farther from the nucleus, which as distance goes up, i.e. goes down. So the farther that an electron is from the nucleus, the lower that the ionization energy is going to be for that. Okay, that's one factor to include. Another kind of jumps into a further development of this model. And I'm going to start over with some representations of this, but I'm going to draw them in maybe a little bit easier way. Lithium, sodium, and potassium. Well, lithium has 3 protons. And the way that I drew it on the previous page, that can be known as basically your full model for your shell model, your full shell model of a lithium atom. Now, I'm going to write +3, and then I'm going to do 1, 2 electrons. Okay. Now, my 3rd electron. And yes, the scale of this has changed. I'm just not very good at drawing. Now, we have our valence electrons, and we have our inner area, which we can call these core electrons. And we can use these core electrons. Basically, every electron that is not a valence electron is considered a core electron. So how many valence electrons do we have for something like lithium? Well, we have 1 valence electron. How many core electrons do we have? 2. Okay. Now, what we can use this for is to come up with what is known as a core charge model. Now, this core charge model is kind of a progression of looking at what are the electrons and what are the protons that kind of are in direct relationship with one another, or directly concerned with one another. Now, with these core electrons, basically what they're going to do is they're going to occupy 2 protons. In addition to that, they are going to be repelling our valence electron. So the way that we draw a core charge model is by taking our number of protons, subtracting the core electrons, and that gives us our core charge. So this model is fairly easy. We're starting with 3 protons. How many core electrons do we have? 2. So what is our core charge? Our core charge is going to be +1. Now what we want to do whenever we are drawing a core charge, or a core charge model of an atom, is we want to write our core charge. And I'm going to go ahead and erase this sodium up here. I'll probably draw that on the next slide, likewise with potassium. So our core charge model for lithium, at its heart, we're going to have +1. We've got one shell, our innermost shell, that we're going to draw as being empty. Our next shell, the one that has our valence electron, we're going to draw that single electron. So this right here is a core charge model of lithium. Okay. Now, here I'm going to draw the core charge model of sodium. Okay, so if you remember, sodium had one valence electron, just like potassium and just like lithium. Sodium had a grand total of 11 protons. So 11 protons minus, well, all of the electrons that are not valence electrons. That, in this case, is going to be 10. If you want a refresher, go ahead and skip back and take another look at that full shell model of this atom. So our core charge is going to be +1. Okay, so now if we want to draw the core charge model of sodium, it's going to be +1. There's our first shell that is empty. There's our second shell that is empty, but how many electrons would it hold? It would hold 8. So our first 2 shells are empty. Our third shell is going to be where we put our 1 valence electron. Okay. Last but not least, the core charge model for potassium. Okay, potassium has 19 protons minus, well, 18 electrons because it only has 1 valence electron. Core charge of +1, so our core charge model is going to be +1. First shell is empty. Second shell that would hold 8 electrons is also empty, so that's 10 electrons. Our third shell, which is also empty, which would hold 8 electrons, that is empty. And it's not until our fourth shell that we draw first electron. So there's a core charge model of potassium. Now, our ionization energy, our IE1 for this, is going to be 418.7. Because we see that drop off. We see an increase in the distance that our valence electron is from our nucleus, and we see that trend as we move across the periodic table. Okay, so now what I want to talk about is atomic radius. And I want to go ahead and do one thing real quick, and that is look at these numbers and cross them out so that we're talking about numbers being in the same units. So this I'm going to write 152, 186, and I believe that one was 231. Okay, so what we're looking at here is atomic radius and basically how large is an atom. Okay, now let's take lithium, for instance, as our example. Lithium, right here, if you were to draw it, you have 1, 2, 3 protons at the center of our atom. We have one electron, 2 electrons, and our third electron in our outermost shell. Okay, so there's our 3 electrons. And so basically what this is, this 152, what that corresponds to is the area in which the largest, or I guess the shell in which this third electron is going to exist, is 152 picometers. So that's a very small unit there, a unit of measurement. Okay, now same for sodium. Sodium's going to have more shells. So if we draw sodium, we've got again plus 11. We've got the inner shell, then a next shell, and then our third shell. All of the electrons are spread out in there. This is not really drawn to scale at all or anything like that, but that's what. This isn't really drawn to scale. If you want some better depictions, you can go to the previous slide, or the previous chunk of this video. The third model here is going to be potassium. And again, it's the same sort of thing. It has a larger number of shells, more shells. So the radius increases. Okay, now with that said, what we've got here on the right-hand side of the screen is we have 3 different ions. Okay, now each of these ions, they also have a different size. So the Li plus ion has an atomic radius of 76, I'm sorry, I read that wrong, 76 picometers. Okay, so what does that actually look like? Well, that lithium ion is going to have 3 protons. How many electrons is it going to have? Well, it's going to have 1, 2. Now we've got both of the, so when we look at this, we have 3 positive charges, 2 negative charges. So we have an ion with a +1 charge. Now, comparing our lithium atom to this Li plus ion, does it take up the same amount of space? No, it does not. Why not? Because this one has no second shell. So that third electron isn't being placed around that nucleus. And so when you think about how much space does this ion take up, well, really you only need to measure the distance that these 2 electrons exist in that first shell. So it's 76 picometers. In addition to that, what do you think is happening in terms of the core charge? So the core charge is calculated by, well, your number of protons minus your non-valence electrons. Okay, so with this lithium ion, we have 3 protons. And how many non-valence electrons do we have? 0. So we have a +3 core charge there. Okay, so what ultimately that means is not only is this ion smaller than the atom, because there's not a second shell, but also each of these electrons, they're going to feel the pull of a maximum of 3 protons. So they're going to be more strongly attracted. Okay, the same thing goes with sodium and potassium. We have fewer shells, but now we have an increase in the number of protons, or a relative increase in the number of protons, or relative increase in the number of core protons. So our core charge is going up. So when we go from neutral to a cation, a positively charged ion, one thing that we see is an increase in our core charge. So what you could say is that if core charge goes up, then our atomic radius goes down. Okay, so on this slide, on this chunk, we're going to be doing the exact same thing. The first thing that I want to do is I want to change my units. That's 66 picometers for the radius of oxygen, 104 picometers for the radius of sulfur, and 116 picometers. That's a 116 picometers for the radius of selenium. Okay, so I've got atoms and ions over here. This is negatively 2 charged ions for oxygen, sulfur, and selenium. Okay, now Before we go on to this, let's go ahead and talk about oxygen. Oxygen has 8 protons and 8 electrons. Oxygen has a tendency to form this O2- ion. Okay, so what does that look like? Let's draw our nucleus, and let's go ahead and completely draw our core model, or our model or shell model of oxygen. I've drawn 3, 6, 7, 8 protons. Poorly drawn protons, but nevertheless protons. Now, with those 8 protons placed, I'm going to draw my first shell. My first shell has 1, 2 electrons. Okay. My next shell for an oxygen atom is going to have 1, 2, 3, 4, 5, 6. Okay, so I've got 6 protons in that second shell, 2 in the inner shell. Now, if I wanted to do a core charge evaluation of this, or core charge model of it, it would be plus 6. I'm sorry. Yeah, it'd be plus 6. Inner shell would be empty. 6 electrons in that next shell. Okay, so what that means is each one of these electrons can feel the force of 6 protons pulling it together. Okay, so the range within this second shell can occupy a space of approximately 66 picometers. Okay, now we've got a balance there. 6 protons, 6 electrons. They're kind of keeping one another in check. Now let's go ahead and draw O2-. What does that look like? Well, it's still oxygen, so it's still going to have 8 protons. So just for the sake of simplicity, I'm going to write 8 plus. I'm going to draw my first 2 electrons in that first shell. My next shell. How many electrons am I going to place? If I have an overall 2- charge, what does that mean in terms of my protons and electrons? That means that I actually have 10 electrons that I need to place. Okay, so I've placed 2 of them. My next 8, are going to be in this next shell. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so 8 protons, 10 electrons. Let's go ahead and draw the core charge model of this. Plus 6 protons, because these 2 inner core electrons are going to cancel out 2 protons effectively. So I have 8 valence electrons. I have 6 protons that are basically visible to those 8 valence electrons. This first shell is going to be empty. The next shell is going to be 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so now if we compare the core charge model of the atomic form of oxygen to the core charge model of our oxide ion, our anion, we've got 6 protons and 6 electrons. If they're kind of keeping one another in check, they're kind of controlling, like each proton has an electron with which it needs to attract. So it's going to be able to, maintain a balance where they're pulling one another, or they're, being pulled toward the nucleus. Now, if we look at the oxide anion, we've got 6 protons and 8 electrons. Okay, so if each proton is responsible for attracting an electron, well, all of these protons here have an increased responsibility. They don't just have to pull one proton, they have to pull more than one, because the ratio is in favor of the electrons. And so what does that mean? Well, that gives an explanation as to why our atomic radius has increased. Because our core charge has remained the same, but the number of electrons that are present has gone up. So you see the same thing with all of these other atoms. If you wanted to draw them out, sulfur and selenium, Well, sulfur is larger than oxygen, which makes sense because it has an additional shell. Selenium is larger than sulfur, which makes sense because it too has an additional shell. S2 minus, what's the core charge on S2 minus? It's still +6. What's the core charge on selenium 2 minus? Also +6. All three of these ions have a core charge of +6 and a total of 8 electrons, 8 valence electrons that they have to deal with. So that's kind of an uphill battle that they're facing. All right, well, I hope that this gives a good explanation and characterization of atomic radius and how it changes based on the atom form, an uncharged neutral atom versus an anion and a cation, and all relates back to core charge. I think that if you draw a core charge model of any anion or cation, you can see that ratio. Think about it as one proton is going to pull one electron. Well, if you have one proton pulling on 2 electrons, then you're kind of going to run into a little bit of a problem. Well, I hope this was helpful, and I will see you in lecture. Have a good one.